joint work with two former undergraduate students at Imperial College called Bastien and Hasan. And this is actually work that was rejected from PLDI 2022, accepted at PLDI 2023, but unfortunately for personal reasons I had to cancel my trip at the last minute, so I'm delighted to be able to present it at PLDI 2024. So, as we heard, the most pernicious kind of compiler bug is what's called a miscompilation bug. This is where you've got a program that is supposed to compute something well-defined according to the semantics of the programming language. Perhaps the program should print the value 42. The compiler compiles the program to an executable, and when that executable is run, something different happens. For example, maybe 17 gets printed instead. So the compiler hasn't done its job properly. It's not faithfully translated the source program into semantically equivalent machine code. These bugs can potentially be disastrous for obvious reasons. A very successful way of finding miscompilation bugs automatically is called random differential testing. This involves making some sort of generator of programs in the language you care about, and using that generator over and over again to randomly generate many programs, feed each program into 2 or more compilers under test, and compile those programs, execute the resulting binaries, and compare the results. And if there's a mismatch between the results we get here, then we know there must be a bug in at least one of the compilers. This is a very popular technique for finding miscompilation bugs. And in my opinion, the most successful example of this technique is the CSmith tool from John Regeer, our esteemed program chair's research group, which was published here in 2011 and won a Test of Time award in 2021. So this is a very successful technique for finding compiler bugs. But the problem is, and this isn't CSmith specific, the problem is that when you generate programs randomly, you typically want large programs to have a good chance of finding bugs. But what you end up getting is massive programs, thousands and thousands of lines of code. And the problem here is that, first of all, you don't know by looking at one of these huge programs which compiler is at fault. So you don't know where you should file a bug report to. But even if you did, you wouldn't be able to realistically solve the problem by looking at one of these ginormous programs. If you would file a 10,000 line program to GCC and say, this program should give this result, but it doesn't, the GCC developers are probably not going to believe you and are going to have a very hard time debugging the problem, even if they do believe you. This is why for differential testing to be effective, it needs to be paired with program reduction, where you have some way of taking an enormous bug-triggering program and shrinking it down to an ideally very small program that still triggers the bug, which developers can act upon. So let's have a look at how program reduction works. I like to think of program reduction being like an axe. And what this axe is doing is hitting the program again and again, lopping off chunks of it in the hope that the remaining part of the program will still trigger the bug. So we lop off a part of the program, make it slightly smaller, and we see whether we still get the mismatch. Much of the time we won't. I'm only going to show you here in the slides where we still do get the mismatch. So we managed to make the program smaller. We lop off a much bigger chunk of it this time. We give this to the compilers under test. They still disagree. Excellent. We lop off some more and some more. And what we end up with is a very small program that triggers the bug in the compiler. We get a mismatch from the results of the compiled executables from this very small program. And this small program will hopefully be small enough that developers can use it to debug their compiler. And the most successful tool in this area, in my opinion, again, is the C-reduce tool, which is from John Regeer, our esteemed program chair's research group, published here in 2012 and won Test of Time award here in 2022. So this is a really great line of work, the CSmith C-reduce line of work. The problem is that actually, if you do test case reduction carelessly, this very small program probably isn't going to be a bug-triggering program. It's probably going to be a program that does something really silly, like declares a variable but doesn't initialize it, and then maybe prints the result of dividing that variable by the difference of itself with itself. This program has got multiple undefined behaviors. It would not be surprising, I didn't try it, but it would not be surprising if GCC and Clang would give different results when you compiled and run this program. And you would not have a good time if you filed a report saying, this program gives a different result with GCC compared to LLVM, there's a bug in your compiler. The problem is that although the initial program may really have triggered a compiler bug, hacking away at the program has very likely introduced undefined behavior, and that's almost certainly going to be why the compilers now disagree on the results that their compiled binaries give for this tiny program. So the problem is that the reducer has introduced undefined behavior. So how does CSmith and CReduce solve this problem? Well, what CSmith generates is a nice, well-defined program. That's a guarantee of CSmith, and that's where the cleverness of CSmith lies. But actually, that well-defined program has got a nasty, undefined program lurking inside it. And what CSmith does is it uses all sorts of cleverness to provide protective wrappers that stop that nasty, undefined program from actually having undefined behavior. So we get this well-defined program from a nasty, undefined core. By undefined, I mean dynamic, undefined behavior at runtime. I'm not talking about syntactic problems or type-related problems, okay? So this is why CSmith manages to work. And just as one example, CSmith would never generate a plain division. We'd never see z becomes equal to x divided by y. It would always generate a wrapped division. We'd have something like z becomes equal to x divided by y, unless y is 0, in which case some default, e.g. x, will be yielded. So this means we can have programs with division, but never unsafe division. This is an example of how CSmith makes things safe. And what CReduce does is actually, when you use CReduce in the context of C compiler testing, you pair the massive axe that is CReduce with a whole plethora of tools that can detect undefined behavior. Valgrind, address sanitizer, the Clang static analyzer, from a C. And in the lovely world of C and C++, because those languages are so horrible but so important, we have an enormous number of these amazing tools that can help us deal with the chaos of C and C++. So this works really well in practice. The problem is I don't live in that world. I live in the world of GPUs, graphics processing units. There are a whole load of languages that are niche but very important. There are compilers for these languages that need to be tested. And there are not, and probably never will be, a plethora of really reliable undefined behavior detection tools for these languages. So what this paper is about is how do you do meaningful compiler testing when you've got undefined behavior but you don't have any tools to help you determine when your programs are hitting that undefined behavior. That's the research challenge that we address in this work. And our idea is very simple. We call it reconditioning. Let me now motivate the idea. In the traditional setup, where you've got a program generator that gives you in one shot a well-defined program that has this undefined program lurking inside it, we've got these protective wrappers that have been generated as part of the generation process. So a very simple insight is, what if we decoupled this? We had the generator actually create the very interesting, weird and wonderful, but probably undefined program. And then we have a separate piece of software called a reconditioner that does a source-to-source transformation that adds the protective layering that's going to make sure this program is well-defined. What benefits might this bring? Well, for finding bugs, it doesn't bring any benefit. What we do is we have our generator roll the dice and give us this probably undefined program. We recondition it, and if we're lucky, it triggers a compiler bug. So this is really just what we had before, except we've separated generate and make well-defined into two separate steps instead of generating the well-defined thing all at once. So no benefit here. But the benefit comes with test case reduction, because now what we can do is, if we've got this not very well-defined program that does, after reconditioning, trigger a compiler bug, we can hack away at the not very well-defined program and make it smaller and smaller, but we could always recondition it just in time before we hit the compilers with it. So we can smash away at this program, lop a piece off, recondition it, give it to the compilers under test. This is now a well-defined program. It's not as small as the badly defined program, but it's hopefully not too much bigger either. If we get a disagreement, that's great. We've preserved the bug. Then we can lop off another piece. We get a smaller program. We recondition it. We give it to the compilers. And again, if they still give us a mismatch, we've preserved the bug. And at the end of this process, what we will get is a small program that probably does exhibit undefined behavior, But because of this process of using reconditioning throughout the test case reduction process, when we recondition this program, we get a well-defined program. When we feed that to our compilers under test, we do get a mismatch, and the mismatch is legitimate, or sorry, it's illegitimate. It's because of the compiler bug. It's not because of undefined behavior, because we reconditioned that undefined behavior away. And hopefully, and it is indeed the case in practice, this recondition program is still very small compared with the original program we started with, small enough to file to developers with a bug report, and indeed it would be this program that we would file when we make a bug report. The compiler developers don't need to know anything about this whole reconditioning business. So that's the idea in our paper, and the contributions of the paper are the very simple idea of reconditioning, which I wish I'd thought of years ago, but I didn't. Practical reconditioning for the OpenGL Shading Language and the WebGPU Shading Language, which are two of these niche but important languages in the world of computer graphics. Effective compiler testing tools based on reconditioning for these languages that find lots and lots of bugs in practice. And then evidence that for these languages, you really do need reconditioning. If you don't use it and just hope for the best, you do, a lot of the time, just get garbage programs with undefined behavior. But that if you do reconditioning, you can still find bugs, you can still reduce them, and developers take these bugs seriously. I've said virtually nothing about what reconditioning actually involves in practice. I gave you that division wrapping example. I can't, in this short talk, give you any more than that. But briefly, there's a lot of reconditioning to make arithmetic safe. We make array accesses inbounds using clamping. We do things to avoid infinite loops. We determinize floating point roundoff error, which is quite important in the GPU computing world. We determinize evaluation order for various operators, and we make sure variables are always initialized. These are easy things to implement. They're, I would argue, much, much easier to do inside a generation tool than to build off-the-shelf third-party tools for detecting undefined behavior. So in summary, reconditioning is a method that allows reliable compiler testing and test case reduction to be brought to bear on languages where we don't have a plethora of undefined behavior detection tools. And in our work, we've shown that this is effective in the context of two different GPU programming languages, the OpenGL Shading Language and the WebGPU Shading Language. And that's as much as we've done. It's unknown whether this would be useful for more complicated languages, like, for example, C and C++, where we don't need this technique because we have all those tools. But would we be able to recondition away some of the more complicated pointer-related undefined behaviors in C and C++? I'm not sure. I think those might be pretty difficult, actually, to handle with this technique. OK, that's all I wanted to say, and thank you very much for listening.
Thank you. We also have 5 minutes for questions.
Nice talk.
Thanks.
And I want to ask, how do you handle randomness? For example, you would have randomness in ray tracing, and it would yield different result every time you run. So it may have different consequences in different compilers.
Yes, that's a good question. When you do differential testing, regardless of the GPU computing world, a requirement is that the programs you work with are deterministic programs. If they're not, then you don't expect agreement between compilers, and you can't do differential testing. You might want to do something like metamorphic testing instead. So that's really a limitation of differential testing, orthogonal to reconditioning.
Great talk. I had 2 questions. First one, how do you get so much energy?
By not sleeping. I'm preparing this talk late last night.
Really? OK. The second question is, this reconditioning, is there a guarantee that it will not change the behavior of the program? Think about it this way. I have a program that I want it to have a divide by 0.
Yeah.
Or things like that. And now, because of reconditioning, can the program behavior not change? Is there a guarantee?
It's a great question. Reconditioning does change the behavior of the program. And reconditioning isn't something we tried to give a formal definition of in the paper. Intuitively, the idea is that you rewrite the program to change it as little as possible, but making sure that there will be no undefined behavior. So, for example...
But are you doing it for C?
No, because for C, there already are all these tools that can detect undefined behavior.
Okay, so which
for
language
C, we don't need reconditioning.
I should have read the paper. I haven't done that. Sorry for that.
We've been doing it for the OpenGL Shading Language and the WebGPU Shading Language.
So if the program has undefined behavior?
Then we recondition it away. So the idea would be you don't have to detect exactly where it's got undefined behavior, but for example, if there's an array access, if you can't statically prove it's in bounds, you take the accessing expression and you mod it by the size of the array, right? That will preserve the behavior of the program when the array access is in bounds, and when it would have been out of bounds, it now makes it be in bounds and gives you some well-defined value where previously you would have had undefined behavior. So you don't want to change the behavior of the program, but in cases where the program would have undefined behavior, you do need to change the behavior because you need to make it defined. Does that make sense? Hey.
Thanks, Ali, for the excellent talk. So is it possible that after reconditioning, the bug cannot be triggered anymore, no matter how you reduce it?
If you recall the workflow, we only find the bugs using reconditioning. So we generate a program with possible undefined behavior, we recondition it, and then ask, is there a bug?
Okay,
so we wouldn't find the bug in the first place. But I think a related question, which is really interesting to me, is does the instrumentation that reconditioning adds maybe inhibit certain compiler optimizations, meaning that there are bugs you're not going to find because you'd need something that was a bit less tame to find the bug? And the answer is yes. And in a different line of work, there's a paper called C-Smith Edge that Christian Carrard did with one of our postdocs, Karine Eva Mendoza. She led the work. And that's all about that question. If you go closer to the edge of undefined behavior, can you find more bugs?
Yeah. So my second question is that it's possible you do this like a reconditioning like statically, right?
Yes.
Is it possible to do it dynamically so that you add as little as possible?
Yes. What we did, but we didn't end up including it in the PLDI paper, was do some dynamic analysis of the program to determine undefined behaviors that are going to be triggered, and then focus on reconditioning those away. And the bits of the program that maybe don't ever get reached because it's a random program, there'll be lots of dead code, leave those alone.
Okay, thank you.
But we didn't find any extra bugs by doing that.
Thank you. Great talk. I was wondering, how do you recondition data races? Because
We don't.
You have read and writes to the
Yeah.
same array, right? So how do you eliminate it?
We don't. So we don't deal with concurrent programs at all. More generally, differential compiler testing for concurrent programs is a really interesting and somewhat open problem because those programs, if they're interesting, are already non-deterministic. So the idea of cross-checking two compilers on a concurrent program doesn't really work because a concurrent program can legitimately give different results every time you run it.
No, I understand. My question was more like you generate a program, right? And that one, it's a data parallel program, but now it has races because you have generated, automatically.
Yeah.
So it might have read-write dependencies and such, which are executing parallel, and now you get. So how do you?
I understand.
Make
An
sure
easy
fix
way
that?
to recondition away data races is to wrap any potentially shared memory access in a big global lock. That won't eliminate race conditions. You'll still have non-deterministic behavior, so it wouldn't help with compiler testing, and it would be a very brutal way of reconditioning. I'm not aware of a less brutal way of reconditioning than that.
Thank you.
Well,
Hi, great talk. So undefined behavior is a bug. Basically, a program with undefined behavior doesn't have any meaning.
Yes.
Is there an argument to recondition all the code that I write? Like, I wrote some program, I don't know if it has undefined behavior or not. I tried my best, but it might have some. So I'm just going to recondition it. In case it does, at least it has some well-defined behavior.
I think that's a really interesting idea. Let's talk about it at the banquet.
Looking forward to it.
All right, let's thank our speaker again.